Hello, everybody, and welcome back to our math class. In today's class, we are going to discuss a very important topic in 3D geometry, namely lines perpendicular on planes. All right. So let's see, what's the definition of a line being perpendicular on a plane? A line L is perpendicular on plane pi if L is perpendicular on any line contained in plane pi. Well, so let me actually do a little diagram here. Well, imagine that this is let's say, horizontal plane, right? Imagine that this is the floor of your room, maybe. All right. Well, a vertical, a vertical would be like so. Well, this vertical is actually perpendicular on every single line that's contained in this horizontal plane. No, all these angles are going to be 90 degrees. We know that at least from some our life experience, no? But quite often, in math, you cannot say, oh, this is this plane. Imagine that the plane is horizontal and this would be a vertical line, so it's perpendicular on everything, no? And actually, this definition is fine, but we cannot act on it, no? Because it says here, line has to be perpendicular on any line contained in plane pi. Well, how am I going to use this idea? Cannot. There's infinitely many lines in plane pi. You cannot just go through all of them. Like I said, there are infinitely many, and then prove that one given line is perpendicular on every single one of those lines. So we have to come up with something better. All right? But before we come up with a theorem proving a workable condition on when a line is perpendicular on a plane, let's actually look at a very simple 2D geometry result that will be very helpful actually. Okay, so look at what result says. It says given a triangle ABC and some point D on BC. Well, okay, here's our diagram. So I've got this triangle ABC, and I've got a point, let's say D on BC, and well, BD is equal to X, CD is equal to Y. Normally this is B, this is C. So we've got this relationship, C squared minus X squared is equal to B squared minus Y squared, no? So C is here, C squared minus X squared is equal to B squared minus Y squared. And the conclusion of this result is that AD has to be perpendicular on BC. So this would have to be a right angle right here, no? Well, what's going on here? Well, okay, what's going on is, well, clearly if AD is perpendicular on BC, no? So if AD is perpendicular on BC, well, we've got here this perpendicular right here. And if we apply the Pythagorean theorem in the two triangles, ABD and ACD, the conclusion follows right away, no? C squared minus X squared, that's actually going to be equal to the square of the height, no? And the square of the height is also going to be B squared minus Y squared. So if D is the leg of the height, then the conclusion follows right away. But is the leg of the height the only position of point D so that this relationship is true? Well, I don't know. Well, that's exactly what we have to prove. Okay, so I'm gonna take just so that we don't get sort of confused by me drawing a perpendicular. Maybe this is our point D right here, no? And the point D will determine an angle alpha here and an angle pi minus alpha over here, no? Well, see in here they're saying C squared minus X squared. Well, that kind of should make us think, well, how about we look in the triangle ABD, right? This little triangle right here, and we can write the cosine law, right? Using angle alpha here, no? So C squared is equal to X squared, okay? Let's say this is Z plus Z squared minus 2XZ cos of alpha. And then if we write the same cosine law in triangle ACD, again, using this time the angle pi minus alpha, so you get b squared is equal to y squared plus z squared minus 2yz cos of pi minus alpha now. And based off of our knowledge in trigonometry, cos of pi minus alpha is negative cos of alpha, so yet a negative sign and another negative sign here. So b squared is equal to y squared plus z squared plus 2yz cos of alpha, no? All right. Well, so now, for example, so let's say this is our relationship number one. This is our relationship number two. Well, in relationship number one, if we move x squared over to the other side, we get c squared minus x squared is equal to, and these are the two terms left over to the right-hand side. So z squared minus 2xz cos of alpha. And if we look in relationship number two, and we actually move y squared over to the left-hand side, over to the left-hand side is b squared minus y squared. So b squared minus y squared, which is equal to c squared minus x squared, no? Which is equal to this. So this is going to be equal to these two terms that are left over to the right-hand side here. So z squared plus 2yz cos of alpha, no? All right. So actually, I'm interested in this equality, and I hope it's clear how I got this equality. So basically, now again, looking at this equality right here, well, z squared and z squared cancel each other. So negative 2xz cos of alpha is equal to 2yz cos of alpha, no? Well, how's that going to happen actually? Well, look, the sign of xz cos of alpha and yz cos of alpha is the same, but in here I have a negative sign here. So one of these expressions is going to be non-negative, the other one is going to be non-positive. Well, if they are equal to each other, the two have to be equal to 0. Well, okay, point D is not equal to B or C, so X, Z, and Y are not equal to 0. So that means that actually cos of alpha has to be equal to 0. So alpha is pi over 2. So indeed, AD has to be perpendicular on BC. All right? Well, of course, if you want this proof to be sort of absolute complete, okay, we can see what happens if point D is on the outside of BC, but you can actually do this, study these cases on your own, and you are going to see what's happening here. And so the conclusion is that AD has to be perpendicular on BC. All right, so I hope this is clear. And this very simple result actually turns out to be quite helpful in us coming up with the little theorem. All right, that's actually very, very important. So here's a theorem that tells us conditions under which a line is perpendicular on a plane in 3D. So look at what it says on here. Line L is perpendicular on plane pi if L is perpendicular on two concurrent lines, no? So we need only two concurrent lines contained in plane pi. Remember, the definition says that the line is perpendicular on a plane if it's perpendicular on every single line in the plane. And that definition cannot be acted upon. You cannot use that, right? In order to actually prove that the line is perpendicular on a plane. But now, if we only have to prove that a line is perpendicular on two concurrent lines in a plane, that we can do in problems. All right? All right. So here's how we can prove this theorem. It's actually a very, very important theorem. Well, look, here's a plane pi. Okay. Here's our plane pi. Okay. And let me draw a line like so here. And this line is perpendicular on two lines contained in plane pi, no? So these two angles are 90 degrees. This will be our plane pi, and this would be our line L. And now, given this, I want to show that this line L is perpendicular on every single line contained in plane pi. Well, so let's actually consider a line contained in plane pi. There you go, here's a line. Well, let's take a point on it. All right. And let's actually draw a perpendicular on this line in this plane. So I'm going to draw this perpendicular right here. All right. And now, well, let's take a point on line L. Let me actually connect these vertices right here. And let me just mark a few lengths on here, okay? So let's say if this is A, if this is B, if this is C, this is X, Y, Z, okay? Let's say this is D and this is E. Well, what's happening here? Well, we've got a bunch of right angle triangles, no? And what I'm going to do is I'm going to write the Pythagorean theorem for literally all these right angle triangles. So for example, in here, okay, we've got a right angle right here. So d squared is equal to a squared plus b squared, no? So d squared is a squared plus b squared, right? In this other triangle right here, again, we've got the right angle, E is the hypotenuse. So E squared is equal to a squared plus c squared. Then we actually constructed a perpendicular right here. So in this little right angle triangle, we can write, again, the Pythagorean theorem, hypotenuse being b. So b squared is equal to x squared plus z squared. And then we've got this other right angle triangle. Hypotenuse of it is c. So c squared is equal to z squared plus y squared, no? All right. What's going on here? Well, let's see. So on one hand, we've got an expression. Okay, let's say this is our relation number one, relation number two, relationship number three, and relationship number four. Well, so if we do relationship one minus relationship three, okay, but now I'm going to say, because I want to write d squared minus x squared, no? So d squared minus x squared, well, d squared is equal to a squared plus b squared. And from relationship number three, x squared is b squared minus z squared, so minus b squared plus z squared, no? All right. Well, b squared and negative b squared cancel each other. So we've got b squared minus x squared is equal to a squared plus z squared, no? Okay, let's call this relationship number four. And now, how about we do relationship number two minus relationship number four? So now e squared, I'm going to say e squared. And from relation number four, I'm going to express y squared. E squared minus y squared is equal to, well, e squared is a squared plus c squared. And from here, y squared would be c squared minus z squared. So it's minus c squared plus z squared, no? C squared and negative c squared cancel each other. So what we get is e squared minus y squared is equal to a squared plus z squared. And let's say this is our relationship number five. All right. Well, looking at relationships 4 and 5, I have to notice that we've got a squared plus z squared and a squared plus z squared. So relationships 4 and 5 together imply that the left-hand sides are equal to each other, no? So d squared minus x squared is equal to e squared minus y squared. Well, let me highlight what's happening here. So d squared, there you go, here's d squared minus x squared is equal to e squared minus y squared, no? Which actually is exactly that relationship that we proved in 2 dimensions, no? So this means right here that if I connect, okay, let's say if this is point capital A and this point right here is capital B, no? If this point right here is capital C and this point right here is capital D, well, based off of that 2D result of ours, we just proved that AB is perpendicular on CD, no? So let me connect A with B. So AB is perpendicular on CD. Well, and how is this useful? Well, actually, we can express AB now. We can express AB from this right angle triangle, ABC, or from the triangle ABD now. So AB squared is equal to, well, again, we've got the right angle at point B. So this is d squared minus x squared. And it's equal to e squared minus y squared, no? Well, how is this useful? Well, okay, ideally, what did we want to prove on here? We wanted to prove that this line L that we started off with is perpendicular on this new line of ours right here. So we wanted to prove that this angle is a 90-degree angle. Well, how are we going to do that? Well, now we have an expression for AB. We have an expression, one of the sides of the triangle is A, another side is Z. So all we have to do is apply the reciprocal of the Pythagorean theorem, no? So if we prove, so if AB squared is equal to A squared plus Z squared, then triangle, well, this little triangle here, okay, let me put another vertex, like so here, this is, let's say X, that would imply that triangle AXB is a right angle triangle, no? And that's exactly what we were set to prove, no? But this relationship is clear, right? Because a squared plus z squared, we have it right here, is equal to d squared minus x squared, which is right here, so it's equal to b squared, no? To ab squared. So that means that we actually proved that this right angle, AXB, is indeed a right angle. So our line L is perpendicular on every single line in that plane pi if it's perpendicular on 2 concurrent lines in the plane. All right? So thank you very much and see you at our next class.